That's the second talk today, in the morning session. The speaker is Professor Bharathwaj Palvannan from Indian Institute of Science. He will talk about Eisenstein congruences and at prime square.
Thanks for the introduction, and thanks to Somnath and Ashay for the invitation. So what I'm going to be talking about is joint work with Jacqueline Lang and Katrina Muller. And this grew out of a workshop program hosted by Ellen Einstein at the University of Oregon. So the setup is we have two primes, P and N, that are larger than phi. And that N is congruent to 1 mod P. And so the motivation comes from an old result of Mazur. So you start with a weight to Eisenstein series at level gamma naught n. So the constant term here is n minus 1 over 24. If you look at the Fourier expansion at infinity, A1 is 1. The nth Fourier coefficient is also 1. And for all primes not equal to n, the Lth Fourier coefficient is 1 plus L. Okay. And so the main motivation is this old theorem of Mazur in 77. In the setup, what he showed is that there exists congruences between plus forms and Eisenstein series. So there exists a cuspidal eigenform. Weight 2 in gamma naught n. That's congruent to this Eisenstein series. So AL is congruent to 1 plus L. So it's the congruence is modulo P, and because you have this cusp form, you have to work with the Hecke eigenfield generated by this F. So you have to choose a prime above P. So you have this congruences for all L not equal to N. Okay, and you say that such an eigenform is Eisenstein at P. And so once you have this sort of question, this sort of theorem, one question that you can ask is sort of a vague philosophical question. Okay, you have one cuspidal eigenform that's Eisenstein at P. One question you can ask is how many such cuspidal eigenforms do you have? So how many weight to cusp forms are Eisenstein? And so one way of phrasing this question mathematically is you look at a rank of a Hecke algebra. So you look at the weight to Hecke algebra acting on all modular forms. And then you look at the Eisenstein localization. And you can ask, what is this rank of this Hecke algebra? Okay. So this. Let's call this R. So Mazur's result, this existence result of Mazur can be rephrased as saying that, well, we have an Eisenstein series and you have at least one cusp form. So this rank is at least 2. And so you can ask if the rank is exactly 2, 3, and so on. And so Merrill gave a criteria for when the rank is exactly 2. So this was in 96. So he gave a criteria that this rank is exactly 2. So I won't state the criteria, but it's in terms of some invariant which people now call the Merrill number. So there's some invariant called the Merrill number. So if this is not a Pth bar in Z mod and Z cross. Okay. And then Lecoultre in 2020, he gave a criteria for when the rank is exactly 3. And again, I won't state the criteria and I won't state the invariant. So the rank is 3 if the rank is not 2. And something he calls a higher Eisenstein element. Is not a Pth bar in Z mod and Z cross. Okay, and these sort of invariants in the literature, these are often called analytic invariants. And so the algebraic side of the story is by Preston and Carl. It's just they just call it analytic invariance. It's just a terminology. So the sort of other side of the story involving algebraic invariance. So this was by Weik and Erickson, Preston, Weik and Carl Wang Erickson, also in 2020. So they were able to count these ranks using something called massive products. So this is not something I want to get into, but I'll just say that these are defined using Galois cohomology. And so this is the sort of algebraic invariance part of the story. And so the reason we are interested in this work of Weik and Erickson is one of the key inputs. So one of the key ingredients is an R equals T theorem. At level gamma not n. Let's say what this is a little later. So they prove some sort of R equals T theorem in this residually reducible case. And so our first sort of goal is, okay, can we prove analogous R equals C theorem? So our first set of goals is to prove analogous R equals C theorems. And okay, so their result was some sort of R equals T theorem at level gamma not n. And so the next question is, what are the levels where you want to prove this R equals T theorem? So if this is our goal, then the natural question to ask is what levels? And so this is some sort of old result of Carayol. So if you look at this associated residual representation, so this is 1 plus the mod p sig atomic character. So in particular, outside P, the team level is 1. And so this is an old result of Carayol that if you're looking for new forms, of level n, but maybe with some exponent, say m, then that m cannot be larger than 2. So I'm not exactly sure of the attribution, but maybe Karyal and Divne. So if you have a new form that is Eisenstein at P, and so I'm only working with one bad prime n, the same bad prime n that was congruent to 1 mod P. And so if you have a new form that's Eisenstein at P, then this exponent can't be larger than 2. So it's either 1 or 2. Okay. So this sort of question, what levels? So there are only four choices. So it's gamma naught n, gamma 1 n, gamma naught n square, or gamma 1 n square. So we wanted to consider R equals C theorems at all these levels. Okay, so in this residually reducible case, one usually considers Galois deformations, but in the residually reducible case, we'll consider pseudo characters. Yeah, P's n and P are at least 5. Okay, yeah. So yeah, I don't know. So I guess for me, at least n minus 1 over 24, and I didn't want 3 in the denominator. Okay, so if you consider this universal pseudo character, so I won't define what a pseudo character is, but it's some sort of analog of the trace of a representation. So I'm interested in the group where the Galois group over Q, where I allow ramification at NP and infinity onto some sort of universal pseudo character, where this universal pseudo character represents so you have some sort of functor from complete Noetherian local rings, which are ZP algebras, and have finite residue field FP. We have a functor from that category to sets, where if you have a ring here, you send it to all these pseudo characters. Which satisfy some properties. So the properties is, so firstly, we want it to be residually Eisenstein. So mod P, this is 1 plus the secatomic character. So the second condition is that so the P torsion points, so the P power torsion points must come from some group scheme. So the condition is that it's finite flat at P. So this was a condition that was sort of formulated by Wang Erickson for pseudo characters. And the analogy to keep in mind is that it's a weight 2 condition. And it's finite flat, so we also want P to be a good prime. So our level is, so the only bad primes is always n. So P is a good prime. And then you have additional condition depending on if gamma is one of these levels. What is? So what I said is that, I'm searching for Eisenstein congruences at level gamma 1 to the n, and that exponent is at most 2. So if your gamma is gamma 1n, then the additional conditions that you have is that the pseudo character, when you restrict it to inertia, sums up to 2. And so this is some sort of, you can think of this as an unramified or Steinberg condition. So you're working with gamma naught and n appears with exponent 1. So it's like maybe 1 star 0, 1, if you want to think of this that way. And then the next condition is that you're in gamma naught, so the determinant is a cyclotomic character. So if your gamma is gamma naught n square, then you don't have the Steinberg condition. So the only condition you have is that the determinant is the cyclotomic character. So this is the periodic cyclotomic character. And if gamma is gamma 1n, and what happens is that when you restrict it to inertia, the character 1 appears as an eigenvalue. So one way of phrasing this is that the pseudo character minus 1, when restricted to inertia, is a character. Okay. So these are some ways in which you can formulate the deformation problem. And so in our setup, the existence of this universal object is due to Weik-Wang and Eriksson. And on the Hecke side, we have this T2 of gamma localized at some Eisenstein ideal. So T2 of gamma is just the ZP algebra generated by the Hecke operators. So TL for all L not equal to N. You look at the UN operator. And if your gamma is gamma 1, you want to also include the diamond operators. And the Eisenstein localization here just means that you localize with respect to the ideal generated by TL minus L minus 1 and UN minus 1. Sorry. So you localize with respect to UN minus 1 if gamma is gamma naught n or gamma naught n squared. Sorry, gamma naught n or gamma 1n. But if you have a square in the level, you just you add UN. So you add UN minus 1 if there's no square in the level, and you add UN if there's a square in the level. Okay, so that's a Hecke algebra. And so the theorem of Weik-Wang and Eriksson is that this R gamma naught n is naturally isomorphic to T gamma naught n. And so this unpublished work of Le Couturier and Weik-Wang Eriksson so they prove that R gamma 1, so it's unpublished, but so they prove that R gamma 1n is isomorphic to T gamma 1n. So our main result is to prove that R gamma naught n squared is isomorphic to T gamma naught n squared. So that R gamma naught n squared is isomorphic to T gamma naught n squared. And so this theorem that R gamma 1n is isomorphic to T gamma 1n, it essentially follows from this previous work of Weik-Wang and Eriksson. So it essentially follows from this, but they have to prove some freeness results over some diamond operators, which I don't want to get into, but I just want to say that the same sort of argument, you can show that this same sort of freeness argument, you can show that R gamma 1 n square is isomorphic to T gamma 1 n square. So for the talk today, I just want to focus on gamma naught n square. So some related comments. So there are R equals C theorems of Skinner and Wiles in the residually reducible setting. So there are these modularity results of Skinner-Wiles in the residually reducible setting. But their deformation object is coming from Galois deformations, and their Hecke algebra is coming from Cuss forms. So as far as I could see, we're not able to prove these precise R equals T theorems using these modularity results. So what we can prove, so if you want to use the modularity results, the best thing we could show is that if R read the reduced quotient if this is known to be finitely generated over ZP, then the best I think we could show using these modularity results is that you can look at the reduced quotient, invert P, and then you get an isomorphism to T after T inverted. So somehow we're not able to prove precise R equals T theorems if we just use modularity results. ZP module. And so I mentioned that one of the motivations was to count ranks, but actually using this unpublished work of Luc-Couturier, so using so the unpublished work of so it is possible to give an expression for all these ranks. So we can count ranks using just the rank over gamma naught n. So somehow, if you're interested in just counting ranks, the gamma naught n picture is enough to count all the ranks. Okay. So one sort of question that you can ask is, are there any applications to these precise R equals T theorems? So our application is reproving a P part of ET and C. But in the abelian setting. So one sort of application is to reprove an old theorem of Burns and Greiter in our setting. So we sort of want to look at this P part of ET and C at S equals -1 for an abelian extension K over Q, which I'll define. So this ET and C at S equals -1, this is also called sometimes Cotes-Sinot. And so this extension is an abelian extension, and K is totally real. And the way it comes up is, so you have that P divides n-1, so you look at the largest power of P that exactly divides n-1. So you have this Q zeta n over Q, which has this Galois group Z mod and Z cross. So there's a cyclic extension of degree P to the M here. So as one application to the R equals C theorem, we're able to show this P part of ET and C for this abelian extension. No. So once you have this R equals C theorems, we know that they're all finitely generated anyway. All I'm saying is that just using the modularity results, I'm not able to even show R red with P inverted is isomorphic to T with P inverted. If I knew that the reduced quotient was finitely generated as a ZP module, then I could show that. But I don't know how to establish anything of that sort. Yeah, I'm not working over ZP tars, and yeah, I don't know how to establish that anymore than what I just said. So this P part of ETNC is already known due to Bones and Greiter. And so their proof uses this Iwasawa main conjecture for GM, yes. So I'll just state this. I'll state the result in a minute. So this uses the Iwasawa main conjecture and mu equals 0. This was due to Maser-Wiles. And mu equals 0 is due to Ferrer, Washington, and Synod. And so, because the main point of our application is to avoid these results. And so the statement of this ETNC in this setup is that you take the set with bat prime n, and then you look at the p-adic places along with it. And so you look at this annihilator. Which, under all the characters of delta, maps to some L value. So this maps to, you look at the L series for -1 to the chi inverse, and you remove the Euler factors at n. So this element, annihilates some H2 group. So there are various ways of, I think, formulating it. So we work with one formulation which makes use of the fact that it's totally real. So it annihilates some H2 group. Over this K, where the module is ZP2. Okay. So this is the P part of ETNC we can recover using this R equals T theorems. So the main sort of novelty, the new thing that we had to come up with is some sort of analog of a numerical criteria. And the main problem we had is that we have not just the Eisenstein series that I wrote down at the start, we have extra Eisenstein series. So we have more congruences involving Eisenstein series, which somehow the numerical criteria was not enough for us to handle. So just some sort of this module theoretic abstract criteria proving R equals T. So the general setup is I have a map from R to T, which is a surjection. And in our case, we have an augmentation, or we have a map to, not to ZP, but to ZP delta, where delta is this cyclic group of order P. So these R and T's are profinite local rings. So ZP algebras with residue field FP. So T is so this is just an abstract setup with rings R and T. Eventually for our applications, we want T to be a Hecke algebra. So the one point which differs from the usual numerical criteria is that we want to impose the condition that T is reduced. Okay. And so the first set of hypotheses that we have, so we look at the kernel from R to ZP delta, and we look at the kernel from T to ZP delta. So the first set of hypotheses that we have is that so this J is the principal ideal. The second hypothesis that we have is that J mod J square is naturally isomorphic to I mod I square. So once we have some sort of hypothesis involving the principality of J and this J mod J square is I mod I square, so then what we have is that R is isomorphic to T. So maybe just as some sort of comparison with this numerical criteria that came up, I think, in Jack Tillewene's talk. So maybe I'll just state the differences verbally. So in the numerical criteria, we don't have this assumption that T is reduced, but we impose a stronger assumption that T is reduced. In the numerical criteria, there's no assumption on this J being principal, but we impose this strong condition. And the main reason this holds in our case is there's a set of bad primes. There's only one bad prime N. So this hypothesis one is some sort of a strong hypothesis that we impose. And it's sort of possible in our case just because we have only one bad prime. So the second hypothesis, some sort of generalization of the hypothesis that appears in the numerical criteria. So this is some sort of, so this numerical criteria only, so it also has a hypothesis, but that only compares cardinalities. But somehow the hypothesis that we require is somewhat stronger. And the main reason is that this sort of diagram that we have in our setup is different from the one that's available in the numerical criteria. So in the numerical criteria, you have a DVR, and you have some sort of augment. You have these algebra maps, and you have augmentation maps to O. So you have O algebra plus O augmentation maps. But somehow we're not able to work with this setup. So we couldn't apply the numerical criteria. And the numerical criteria also has a strong conclusion that these rings are complete intersection rings and Gorenstein. And so we don't have those sort of conclusions. Okay, so the point is that we want to show R equals T. So we want to show R equals T. So we want to establish hypothesis. The goal now is to establish hypothesis 1 and hypothesis 2. So those are the two things we need to establish. And usually how this works is you do some computation on the Hecker side and you do some computation on the deformation theory side. So on the Hecker side, it's essentially a computation due to OTA. So on this gamma naught n square, so you have this n stabilization of the Eisenstein series. Where the TL eigenvalues are still the same. And the UN eigenvalue, you remove the n term, so the UN eigenvalue is 0. And for every chi, which is non-trivial, that factors through delta. You can form this Eisenstein series E chi inverse chi, which is again an Eisenstein series in gamma naught n squared. And so for these Eisenstein series, the an eigenvalue is 0, and the Lth eigenvalue is chi inverse L plus L times chi of L.
But here you are this theorem for n.
This, yeah, because like n squared doesn't have any more p. Yeah. Yeah, so I'll write down the annihilator, and then you'll see that the annihilator. So I want to write down a congruence ideal, which has a generator that looks very much like this theta, et, and c. So that's how this. We have to work with n squared. Yes. So the main point that we have to work with n squared is that we have to look at all Eisenstein series, and these Eisenstein series, they have level n squared, E chi inverse and chi. So somehow to accommodate all the Eisenstein series, we have to work with level n squared. Yeah, so the goal is to package all this information together. So you package this using this sort of map from the ring map from T to ZP delta, where the UN eigenvalues are all 0. So now where do you send TL? You want to send it to a grouping-like element. So you have Z mod and Z cross, surjects onto delta. And so like an L goes to a grouping-like element, which I'll just denote it this way with these parentheses. So it's 1 plus L or chi inverse L plus L times chi L. So what we want to send it to is this grouping-like element L to the -1 plus L times the grouping-like element L. So this is what we want to send it to, but one technical point is that I have to consider an automorphism. So I'll just pick a U is that 2U is congruent to 1 mod P to the M. So morally, I just want to send it to this grouping-like element inverse plus L times the grouping-like element. But just in this business, there's one technical point where I have to consider a permutation involving this U. So it's L to the minus U and this grouping-like element L to the U. Okay. So what happens in this case is, so again, this has come up, I think, in Jack Tillery's talk. So in this business, we want to consider congruence ideal. So we have this map from T to ZP delta. We've taken care of all the Eisenstein series. What's remaining is the cuspidal part. And so this push-out diagram is ZP delta modulo the congruence ideal. And this is isomorphic to the cuspidal Hecke algebra modulo what's called the Eisenstein ideal. And so the goal on the Hecke side, the goal of the Hecke side is to show that the congruence ideal is principal. And computer generator. Okay, so the point is that eventually I'll want to handle Selmer groups, which are of the form the sigatomic character times the tautological character. But if I had L inverse and L, what happens is that the extension involves the square of the tautological character. So I just wanted the tautological character, not the square. In this method of Ribet, you produce extensions one by the other or the other by this, and so I wanted one and not two. Okay. So I think I won't do the computation involving the residues, but it's essentially done by Uta, and the whole goal is to just package all of them into one thing. So the story is that so you use some residue computations of Uta. This is in 03. To interpolate and to show that the congruence idealist principle. And the second set of ingredient is so you also want to show that this the thing that you interpolated is it's an integral element in ZP delta, so you can use the second Bernoulli polynomial. Which is available because we're working over Q and looking at abelian extensions. So you can use the second Bernoulli polynomial to show integrality. So the main point is that we have some analytic object or ZP delta. Which under this sort of decomposition, it sends it to an L value. So it sends it to L minus 1 comma chi, along with some fudge factors. So the fudge factors involve some Gauss sums. So tau is some Gauss sum. And chi is not trivial. And if it's a trivial character, you send it to 1 plus n over 2n times 1 minus n times the Riemann zeta function at minus 1. Okay. So the Riemann zeta function at minus 1 with the Euler factor at n removed. For all the other functions, so the chi's are factoring to z mod n z cross, so the Euler factor at n is just 1. So I think here's maybe the answer to maybe Masato and Kazim's question. So I really wanted to, at the character chi, I really wanted to see something involving chi and not chi square. So that's why I needed these sort of extensions. And then maybe, so you can see that this data analytic is very close to the element that appears in ETNC. There's only a minus 1 that's not appearing, and there are these fudge factors in front. So it's almost that, but not quite that. Okay, so these are the computations on the Hecke side. And on the deformation theory side, we have to work with GMAs. So again, our goal is to show R equals T, which by this abstract criteria boils down to verifying these two hypotheses at the end. So I'll just write down the ingredients. So you have the pseudo character, this universal pseudo character, and you want to work with the GMA. Associated to that, so generalized matrix algebra. To this universal object. So it's almost like a 2 cross 2 matrix. The B and C, where somehow one of the R's corresponds to the mod P atomic character globally, and the other R corresponds to the trivial character. And sort of this universality of this R uh, can be used to show that so J, which was defined as the kernel of the map from R to ZP delta. So in this case, it's also the reducibility ideal for this GMA. And so in this business of GMAs, when you have the reducibility ideal, these sort of fractional ideals, if you will, this J equals B times C. So the main object is, so we want to use Ribet's method. So we want to have some Selmer groups. So you look at this tautological character into ZP delta. And this sort of cyclotomic character that we had. And so we want to produce elements in some Selmer group. So we have some sort of discrete modules. One for the inverse of the cyclotomic character, and one for the cyclotomic character. So it's over ZP delta, twisted by this character. But because it's discrete, you have to tensor it up with QP mod ZP. And similarly for the cyclotomic character. And in this business, you have to produce, construct some Selmer groups following Greenberg. So we construct some non-primitive Selmer groups. This is following Greenberg. So I'll just call it Selmer group. So the non-primitive Selmer groups usually have this superscript sigma naught. So for both of these discrete modules. And again, I won't define them, but these are just some subgroup of a global cohomology group. These are global cocycles with some local condition at P. And this local condition actually comes from the fact that our deformation problem, the condition at P was this finite flat condition. So it's some global conditions with some sort of finite flat condition at P. And so we really need this finite flatness to first show that on the one hand, for this inverse of the cyclotomic character, there's actually no condition, it's just locally trivial at P. But for the cyclotomic character, you have some condition that comes from Kuma theory. And so here we really use both Selmer groups and use the fact that it's finite flat at P. And so once you have these Selmer groups and these GMAs and these congruences between Eisenstein series and Cusp forms, we want to use Ribet's method. And we use this version involving GMAs of Bellaish and Evier. So these Selmer groups, the dual of the Selmer groups surject onto C mod JC, and the dual of the Selmer groups, the other one, surjects onto B mod JB. And so Carl and Preston also study similar Selmer groups, but not over ZP delta, but just over ZP. So they show that similar Selmer groups for QP mod ZP for the inverse of the cyclotomic character and QP mod ZP for the cyclotomic character. So these Selmer groups are cyclic ZP modules. So this is something Carl and Preston show. And so using the cyclicity, what we can show is that our Selmer groups over ZP delta are also cyclic ZP delta modules. So then using some control theorems, Nakayama lemma. So what you can show is that our Selmer groups are also cyclic ZP delta modules. And then this surjection from, you can use the cyclicity and this surjection that's available using Ribet's method to show that C and B are principal. So this sort of cyclicity tells us that B and C are principal. And because J is B times C, then J is also principal. And so this was hypothesis one. But something stronger is true for the Selmer group for this inverse of the cyclotomic character. So you can use this Greenberg's cohomological criteria for freeness. To show that this Selmer group for the inverse of the cyclotomic character. So it's a cyclic module. So it's ZP delta modulo some ideal. But what you can show is that that ideal is actually principal. So it's generated by some element, which I'm calling theta algebraic. And then finally, what's true is that because our GMA was faithful, and because B and C are principal, so what you can show is that this C mod JC that appears in Ribet's method is actually just isomorphic to J mod J square. Because our second hypothesis involves J mod J square. So somehow I need to get this J mod J square. I'll just take maybe 3 more minutes. So now just putting everything together. So on one hand, we have that ZP delta modulo theta algebraic. This is isomorphic to the dual of a Selmer group. Which surjects onto C mod JC, which by this faithfulness and principality argument is just J mod J square. But this J mod J square surjects onto I mod I square. So remember this I was nothing but the kernel of this map from T to ZP delta. And then we had this sort of projection onto the cuspidal part, where the quotient by the cuspidal part is given by the Eisenstein ideal. And this is ZP delta mod theta. So because this I is entirely in the cuspidal part, this is actually isomorphic to the Eisenstein ideal modulo the Eisenstein ideal square. But this principality of J tells you that I is principal, which then implies that the Eisenstein ideal is principal. And so this just is isomorphic to the cuspidal Hecke algebra modulo the Eisenstein ideal, which is isomorphic to ZP delta modulo theta analytic. So we have a bunch of arrows, some surjections, but just putting everything together, we have a surjection from ZP delta modulo theta algebraic. It surjects onto ZP delta modulo theta analytic. And delta was Z mod P to the MZ. So ZP delta is a local ring. So that surjection just tells you that this theta algebraic is some x times theta analytic or some x in ZP delta. But under the augmentation map, so both theta algebraic and theta analytic. So using this result of Weck-Bang-Erickson, if you will, both of these elements map to n-1. So both theta analytic and theta algebraic are mapped to n-1 up to units. And since ZP delta is a local ring, that just means that X is unit. So that means that you have an isomorphism here, which means you have isomorphisms for all these surjections. So in particular, you have the isomorphism from J mod J squared to I mod I squared. And this was our hypothesis too. And so that shows R equals T. Yeah, I'm done.
Thank you very much. Other questions or comments? Okay, then let's thank the speaker again.